Okay, all right, let me share my screen. I prepared quick repo. And up. All right. Can you properly see the screen? Can you read what's on the screen? Is it clear? Okay. All right. So thank you for having me. I'm excited. I hope it's going to be useful for some people to. So the goal here right now today is to learn the basics of assembly in Solidity, which is called YUL. And that's it. And if we, so I think I'm going to start with a quick introduction to YUL, which should take like 5-10 minutes. And then what I thought could be fun is we're going to solve one of the DamnVulnerableDefi challenges. I chose randomly one which was not too hard, like pretty easy to solve. So we're going to solve this one in assembly. All right. And if you, I mean, if someone has any question, feel free to interrupt me. If it's not like I don't want the talk to take like 2 hours, but if you have like a quick question, definitely interrupt me and I will answer. Okay, so let's start. So first of all, YUL. Here, so I'm in the Solidity documentation. Here you have all the documentation for YUL, and you can find like a lot of really interesting stuff if you're learning. So you should definitely read that if you're a beginner. And one of my favorite websites to learn about the opcodes and what you can do in YUL is evm.codes. So I definitely recommend it. Best resource. So we're gonna start easy. So I prepared like a quick repo for the DamnVulnerableDefi challenge, but first let's start in Remix. So in Remix, we're gonna override this one. YUL, and we're gonna do like a few stuff with YUL. So we're gonna keep it like that. This doesn't matter. Okay, so what are we gonna do? We're gonna first learn how to declare a variable in YUL. We're gonna change a storage variable also, and we're gonna call another contract with YUL. So those are like the most basic stuff you can do. And once we know how to do that, we're gonna be able to solve the DamnVulnerableDefi challenge. Okay, so let's have a function, let's call it OpenSense. And let's write our first assembly block. Okay, so to declare a variable in YUL, you can see it here. So here you have like the syntax on how to, what to do in YUL. To declare a variable, you just use let, the let keyword. The $2.equal is to assign a value, and that's it. So we're gonna have, we're gonna create like a simple variable, and we're gonna assign it a value of 3. Okay, that's it. We have a variable A. Now we can do some comparison stuff with it. Like we can write an if, and we can say if our A is lower than 5, for example, we want our contract to revert. So we're gonna revert. So how do I know how like lower than and revert work? I just go here. Here I have the lower than operator. It says that it takes as input 2 variables, and it's going to output here, it's going to output either
Oh my
1
god,
or 0.
man.
Okay, so basically it's just like a classic if. So if it outputs 0, it's not going to enter the if, so it means that A is over 5. And if a is lower than 5, it's going to output 1. So it's going to enter the if, and it's going to revert. And same for revert. How do I know which variables, which input I'm supposed to put in? I do the same. I go here on event.code to revert. And revert, it takes two inputs. First, the offset, which is the offset in memory, where I have the data that is going to be reverted with, and the size of the data. Okay, I'm going to come back to that after, and we're going to revert with some data just to show you how it works. Okay, this can be yours. Okay, and we have our first assembly block. Now let's compile and let's deploy it and call our function. And as expected, it reverted. Okay. What's really cool with the Remix, I mean, I'm sure if you're all learning right now about assembly, you already know that, but I'm just going to say it anyway, is the debugger. So you can debug and go step by step into the code. And so you can see here what's happening. And you can see we have our opcodes here, like every operation is here. Our stack is here and our memory is here. So if I go through the code, I have, so for example, you can see here I have 3 on the stack, which is our a variable that we just declared. Right now it's going to push 5, which is our value. And okay, so let's push the 5. So the 5 is here on the stack now. And it's going to duplicate, so dev.to, which means it's going to duplicate the second value on the stack, so the 3. So basically it's copying the 3 just before it pushed the 5, and then it's going to compare the two values. So we duplicate, and then it's going to apply the lower than operator to those two values. So let's apply it. And we see that it outputs 1. So it means that a is indeed lower than 5. Then it's going to check the return value of lower than with is 0. So again, you can check is 0 is, you're going to see that a lot in YUL. So is 0, it's basically taking an input and just checking if it's a 0 or not. So it's checking the value, and based on the value, it's gonna go in the if and revert, or it's just going to keep on executing. I hope this was clear. Now let's do some just a bit more complicated stuff. So let's call another contract. So we're going to create another contract. Call this one first. Let's call this one second. And let's have a function. Okay, let's call this one call open sense, and let's call this one open sense. And this one is going to return a value. Okay, so this is actually, and here we're going to call our contract OpenSense. So what I like to do before going into assembly usually is just to test with Solidity, pure Solidity, if I didn't do a mistake. So let's, we're going to deploy to create the contract in Solidity. We could do it in assembly. Maybe I can do it just after if someone wants to. So we're going to have And by the way, again, if I'm making, so I'm writing and speaking at the same time, so I could make a mistake. If I make a mistake, don't hesitate to open your mic and correct me.
Awesome. Thank you so much, bro. You're doing great.
All right, cool. Okay, so we're gonna just call OpenSense on second. Uh, let's make this one view. And it's supposed to return a uint. So we're gonna put that in a result variable. And then I'm going to import the hard hat console so we can log, which is going to make everything more understandable. So we're just going to log the result. And let's try it. Okay, we just compiled. Now let's deploy our contract and let's call. Okay, we have result 7. Okay, so in Solidity, we are good. Now, let's take like a intermediary step, like in between Solidity and YUL. What we can do is basically what we're going to do in YUL, in assembly, to call a contract is we're going to encode raw call data and just use a low-level call, which I'm going to show you. We're going to use the low-level call function and pass it the raw call data. Okay, so what I'm going to do is I'm going to take an intermediary step and just do this in Solidity first. So I'm going to use for that, I'm going to use ABI encode with signature. So I'm pretty sure most of you know that. If you don't, just go in the Solidity doc. So we're going to encode we're going to get basically the function selector of this function. It doesn't take any arguments, so we don't need that. And we're going to store it in no, of course it's not. So open sense call data. So we have our call data here, and now we are going to call on the second contract. We're going to use the low-level call. Actually, since this is a view function, we don't need call. We're going to use static call, which is a view call, basically. So it's not we're making sure we're not modifying any state. So we're going to use static call with the open call data. And this, so this is supposed to be called on an address. And this returns a Boolean and the data. Okay, so let's try it and let's log our result and the data. Okay. See, okay, so I just compiled. I'm going to deploy and call. And we see that it's succeeded. So it's true, like the success for Boolean is true. And the data is 7 as expected. So we have our data correct. We get our data correctly. Okay, now let's do the same thing in assembly. So we're gonna first encode with signature, but in assembly. So to do that, we're gonna store in memory. So with mstore, it stores at a specific place in memory. So here at slot 0, we're gonna store that string in memory. So here, basically, from starting from slot from a memory index, sorry, 0, we have the string OpenSense stored. Now we're gonna hash basically a function signature. Again, if you don't know that, you can go in the Solidity documentation. It's explained. So a function signature is a hash of a function selector, sorry, is a hash of its signature. So the signature of this function is just the name of the function with the parentheses. If it had argument, we would put the argument here with separated by a comma without space. So for example, like that. We're going to see it after. We're going to code some functions with arguments. So basically, what we're just going to do is going to take the hash. So we're going to store again. So we are going to override our string and store again at 0, but this time the hash of our string. So our string is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it's 11 characters long. So basically we are saying, go to memory index 0 and take 11 bytes and hash those. And then the result of this hash, you store it at index 0 in memory. So we're going to have, okay, I'm going to show you something. I'm going to show you what it looks like, what we have. What I like to do usually is I use bytes, since the memory works in Solidity, the memory works in bytes 32, in the EVM, sorry, not especially in Solidity. So I just put some bytes 32 and then I log them. So it helps me to see what is the current state of my memory. So I'm going to put in my A here what's at index 0 in memory, and these 32 bytes. So mload is going to load 32 bytes of memory. So let's see. Let's deploy, and then call. So you see that I have, so this basically is the hash that I just computed here. And the function selector is just the first 4 bytes of that hash. So this is going to be our function selector. Okay, so we're good. I can remove that. And now we are gonna do our static call to the second contract. So to do that, we use the static call opcode, and it takes a few inputs. So again, you can go on the website and read about it. It takes the amount of gas you want to pass it, which address, which contract it's supposed to call, where is the data stored, so the call data, and where do you want, if it returns a result, where do you want it stored? So we want, let's do it. We want to pass all the gas available. We want to call second. So second is a state variable. So we're going to have to load what's in that state variable. So we do sload. So again, sload is a state load. It's loading a variable from the state. Second, and you can just access state variables just like that in assembly. In sload, it takes the slot number that you want to load. So you have a special keyword in assembly that is slot. So basically, we are saying just load what at the slot at the second. I mean, it's taking the slot number of the second variable and passing it to sload and loading what's at that variable. So it's basically the address of the contract. Okay. Again, I'm going pretty fast, but if you want more details,
No
you can check.
worries, no worries. You're doing great. Everything's recorded, so people can always go back. Okay.
All right, yeah, that's true. That's true. You can pause the video and go check the documentation. All right. So next, again, we can check here. It's checking where the offset of the call data is. So since we stored it at 0, we're gonna say 0. How big is the call data that we want to pass? Again, we would just want to pass the function selector. So it was 4 bytes. And then the result, we're going to store it again at 0. So it's going to override our hash that we computed, but we don't care because we don't need it anymore. So we are going to override it with the return value. And how big is our return value? So our return value is a uint 256. Uint 256, again, in the EVM, all these variables are 32 bytes. So we are going to get 32 bytes of return value. We're going to check if the call was successful or not. So this is what static call, you see it returns success or not. So we already had success here, so we're going to call it success 2. And that's it. Oh yeah, and then let's load, of course, let's load the value. So we are going to have our return value, which is a uint 256, and we are going to call it, again, we had a result here. I could just comment all that. I'm going to comment. Up, up. So this is result, and this is going to be just success. And we're going to assign to result what is currently at index 0 in memory, because again, we stored what was returned from the function at index 0. So we're going to get it in result, and then we're going to log this, and we are going to log up. And we, of course, we don't have access to success, so let's put it here. Yeah, because obviously everything is block scoped, so everything that you declared here is not accessible outside. So what you can do is just declare it before, and then you don't need the let keyword. You just assign it to the variable. Okay, so that's it. This here we don't need it anymore. Let's deploy and call. And you see that the call was successful and the result is 7 as expected. So that's it. That's how we make calls in assembly. And now, so that was a static call, but if you want to make a regular call, it's you just call the call opcode, and you just have to pass how much ether ways you want to send, but it's basically the same. But we're going to see it right after in the DamnVulnerableDefi.
Awesome. Can I make a question?
Yeah, of course.
Regarding the types, right? Inside you, I can only work with uint 256, right?
Yeah.
And
So yeah, everything. Yeah. Yeah, say it. What's your question?
so yeah, my question is regarding you. I can only work with uint 256, right? I cannot do another type, right? Like uint 8 or something.
No, you can do whatever you want. You can pass. I mean, you're right. Um, everything. Yeah, everything works in 32 bytes. But you can, for example, there are in the memory. You can go. Let me show you. You can work in 8 bytes also. So actually, it's not even. It's not. Sorry, it's not 8 bytes. It's 8 bits, which is 1 byte. So you can work byte by byte also.
One question that I have for you too is regarding the optimization. Is it true that not every time using assembly will give you more optimized code because, the optimizer is just too good, for some things? Or it's always better to implement, or I mean, it's always faster to implement your own solution in assembly?
I mean, faster, I don't think so. I mean, I think it's faster to code in Solidity and you would make less mistakes. But is it cheaper? I think
When I
I
when I when
can
I say
think.
faster, I mean it's more efficient.
Okay. So yeah, for me, it's if you know what you're doing and if you want to optimize to the maximum, it's always going to be better in assembly because you control the raw opcodes and you know exactly what's happening. If you use Solidity, there are some optimizations that are going to be made in the background or some checks that maybe you don't need and you don't want. So it has to be cheaper in assembly. But of course, like you could make some mistakes and you could have some security issues. So you have to be really careful. All good? All right, cool. Yeah, anyone has like a quick question or should I just keep going?
now. His question is, if you use the via AR to compile, would you get a similar optimization? So what will the intermediate representation give you a similar optimization?
Yep, probably. I mean, it's supposed, yeah, it's supposed to give you, it's giving you basically the optimized assembly, like a YUL version. So it might do some more checks and things in the background. So you might have like a more how do you say, like a bigger code, kind of like this might be the quickest way to get there, but via IR should be like pretty close to that, I think. Good.
Awesome. And we have another
All right.
question from Kuririn that
Yeah.
says, so let inside you gives you 156 type because type is not declared.
Yeah, basically, yeah. So let is going to where is my let? Oh yeah, I removed it. I declared it before. But let basically is adding a variable to the stack. And since the stack, just like the memory, works in blocks of 32 bytes, so 256, yeah, it's going to give you a 256 variable. But I mean, it's a block of 256 bits. But if you want to assign it to a uint8, for example, you can do that. Like, it's not a problem. You can assign it to a uint8, but you have to be careful. Like, if you overflow the uint8, it's going to cause you issues. But it's so if you create it here, it's going to be a 256, but then you can do whatever you want and just assign it to a uint8 variable. It's not a problem. But again, that's the big difference between assembly and Solidity, is that there is no check here. So that's how you could easily make a mistake. Okay, we keep going. All right, cool. Let's do it. Okay, so we're gonna go and try to solve this challenge. So, um, so this is the third challenge of DamnVulnerableDefi. So we have it's a lending pool that is giving flash loans, and we're gonna try to abuse it. So let's look quickly. Actually, let's do it here directly. I copied the concept. Wait, what do you mean? We are going to solve it, so it's going to. Yeah. Sorry, you're talking. Sorry. Yeah, I forget all the time that it's going on YouTube. So yeah, obviously, if you're watching on YouTube and you haven't solved the challenge, try to solve it first and then keep watching the video. Yeah. Thank you. Sorry. Okay, so I prepared like a quick repo with a Forge Foundry installed. I copied the two contracts from DamnVulnerableDefi. So there is a valuable token that is here, and our truster lender pool that is here. So this is, and then we have a Forge test. I'm going to open my terminal and see. And so we have a test, so basic Forge test. We have our player here that I created. Then I just set up so basically, if you know DamnVulnerableDefi, it sets up everything, and then you write your code and it checks after. So we have our setup here. So it's exactly the same. You can check afterwards if you want. And then we're gonna solve it here, and I'm gonna add after the checks. Okay. So let's just solve it in Solidity first. So we're gonna go. All right. Completely and solve it. Okay, let's check that our forge test works. Okay, let's put it the logs and put it in watcher mode. Okay, we are ready. Okay, so how do we solve the challenge? I'm going to go pretty fast. So it allows us to take a flash loan. We can pass an amount, who is the borrower, and then we can make this pool call any contract, so a target contract, with any data that we pass. So what we're going to do is pretty easy. We're going to do a flash loan with a zero amount. We're going to loan nothing, but then we're going to make it call, because the goal of the challenge is to steal all the tokens from the pool. So we're just going to make it call the token contract. So this is going to be the target contract, and make it approve the player, so that the player can just then transfer everything from the pool to itself. Okay, so how do we do that in Solidity? We are going to call pool that flash loan. So we said we want to call it with zero amount. The borrower is the player. The target is the token contract. And we want to pass some call data. This is going to be the call data. That is going to be the approve function. So we are going to first have to encode our call data. So let's call it approve call data. And this is going to be ABI encode with signature. So as you know, the approve function in ERC20 is taking the address of the of the person to approve and the amount to approve. The address is going to be the player's address, and the amount is the tokens, the total tokens that are in the pool. So, okay, so this is the call data that we're going to pass, and basically it's going to make the pool approve the player. And then sorry, just to check. Oh yeah, of course. And then the player is going to sorry, the player is going to call the transfer function and transfer the funds to himself. So all of this is going to be called by the player, and the end of rank. And the player is going to call the token transfer from pool to himself and the value. Okay, let's see. Let's run it. Okay, we don't have any errors. That's good. Now let's make the checks. Let's check the balances at the end. So we want final checks. We want first the balance of the player to be taken in pool. Yeah, makes sense. We want the player to be this, and the balance of the pool to be 0. Okay, so I think we are good. If I made a mistake, say it now, otherwise I'm gonna keep going. Okay. Okay, now, good? All right. Okay, now let's do something a bit more difficult, obviously, and let's try to solve it in YUL. Okay, so we're gonna crank the player again, and we're gonna copy this because we want the checks to be done at the end. Up, we're good. Okay, and obviously it fails because the checks, we're going to put them back after. Okay, let's do it. Okay, so same thing. We want to do the exact same. We want to have the exact same flow, but in YUL. I'm going to do something. Actually, I'm going to have the same thing that I did before in Remix, where I did the intermediary call. I'm going to do the same here. I think it's going to make it easier to understand. So here, instead of pool.flashloan, I'm going to encode the flash loan function. And bytes. So you see, I'm passing the signature of the function, which is here, and I'm encoding it. I'm encoding the data, the call data, and then I'm just going to use the low-level call to call flashloan. So this is going to be flashloan data, and the values are the same here. This is our flashloan call data, and then I just have to do. I just call pool dot call. I pass the call data and I check if it's successful or not. Actually, if it's successful, then it's going to pass the test. If not, it's just going to fail. So I'm just going to code it like that. Up. And of course it fails. Okay. Okay. I made a mistake. You see, you can easily make a mistake. So this is the flash loan is with a capital L, and I was putting a, I think that's the mistake. Okay, let's try it again. Yeah, exactly. That's a really good reminder, actually. Yeah, you have to make sure like that the name of the function is exactly the same and that all the arguments are passed in the right order with a comma and with no space. So you see here it passed, but if I put a space here, then the signature of the function is going to be different. And so the selector is going to be completely different. And it's going to try to call a function that doesn't exist, basically. You see, it's trying to call this function 6a14fe, and it doesn't exist. The function that I want to call is this one. If I save it again, then we're good. All right, perfect. So this I can remove. This, let's keep it like that. And that's it. Okay. So now let's do the same with YUL. So first, let's encode. So let's go with the same steps. Actually, let's first encode our approved call data. Now we know the steps, so it's going to be easier. So we want to encode this. let me think. I'm going to put, okay, so I'm going to introduce like a new thing. I'm going to use the free assembly. I'm going to use the free memory pointer. So free memory pointer is basically in the EVM, it's a value, a special value that is stored at in memory at index 0x40, which is 64. So in hexadecimal it's 0x40, but in decimal it's 64. And at that index, there is a special value that is stored that tells you where is the next free memory slot. So where you can use the memory freely without overriding anything. So I'm going to store everything at the free memory pointer. So I'm making sure I'm not overriding anything. So we are going to store this. So we are storing at FMP, so at the value that is returned here, so we know that is safe. We're going to store approve. Then we need to hash it. So how big is it? So you see, this is, you can see here at the bottom, it's 24 characters. So we are going to store the hash. Sorry. So at FNP, we override it again, just like we did before. We were restoring at slots at index 0. Now we store at a free memory pointer. Now at the free memory pointer, we have the hash of our approve function. And then we're going to do something new that we didn't do before, is we're going to store our arguments. Okay. So again, remember that we have the hash at FMP, and we only need the first 4 bytes. So we can override the rest of the data, because the call data, remember, it's going to be so the function selector and then the arguments. So address or uint, then they are going to be stored right after in the order. So here we are going to store at FNP plus 4, because we don't want to override the first 4 bytes. At FNP plus 4, we are going to store the address, which was, I'm getting confused, sorry, which is the player's address, because he wants to approve himself. So player. Again, just like we saw before in Remix, player, it's a state variable. So we can't access it just like that. If we do that, this is going to fail. It tells me, okay, this is a good explanation actually. So to access storage variable, just use the slot and offset suffixes. So we're going to use the slot suffix, and we are going to load sload that variable. So we are getting the value that is at player and storing it at FMP plus 4. And then we want to store at FMP plus, so at FMP plus 4, we have that value. And then so that value is 32 bytes. Again, everything works in 32 bytes. So we are going to add 32. So at 36, we are going to store the next value, which was tokens in pool. And this is not a state variable because it's a constant. So it's considered as a regular variable. So you don't need to sload it. So I think we are good. Let me think for a second. No, we are not good actually, because so those are bytes. And let me show you how bytes work in the EVM. Okay, here. Dynamic types. Okay, so bytes, in the EVM, they are encoded in a special way because since bytes can be just like strings, so strings and bytes are the same. Strings and bytes, they can have like a random size. Like you never know what size it's gonna be. So they are encoded in two parts. So first, in the first part, it specifies the length of the bytes, and in the second part, it's going to be the actual bytes, which can be any length. Basically, it's going to be at the length of that is specified here. So you see here, for example, for hello world, this is 13 characters. So you encode first the length, so D, which is 0xD, which is 13 in hexadecimal. And then you have the string, which is hello world in hexadecimal. Okay. So first, so what we missed here is that we need to encode the length of our byte first. Otherwise, we're never going to know. It's not going to be clear like how big it is. So we have to add something here. So add the free memory pointer. Basically, we're going to encode the length of what we had here. So here we had, you remember we had 4 of function selector, 32 bytes of player's address, and 32 bytes of tokens in pool. So this is in total 32 plus 32 plus 4. So this is 68. Okay. And then we are going to move everything by 32 bytes since we had in that store. So we are going to add here 32. And we're going to add here. Oh yeah, we have to be careful here because now it's stored at 2. Actually, what we can do, we're going to make it easier. This, we're going to store it at 0. And so that here you can just use the hash. So we store the string at 0, but then the hash, we store it obviously here at 32, at FMP plus 32 because we need it. So 36, so we add 32, and then 36 plus 32 is 68. Okay, now I think I have my bytes, and we could actually check it. Okay, let's save and make sure everything goes all right. Okay, we could check it by just logging it. So we could, it's memory, let's call it, how did we call it before? Approve call data. And then we're going to make approve call data is equal to the free, it's like the same memory address. We're making it basically say approve call data is the same as a free memory pointer. And then we are going to log it and see if our call data is right. And we're going to compare it with this one and see if they match. And of course they don't match, but I know why. Okay, so log by console.log, it touches the memory also, so it's going to change the memory, but since it's going to use the memory, but since we modified ourselves the memory, that's also that's actually a good thing that it happened. You really have to be careful when you're using assembly that when you're touching memory, you're not you put it back in the way that it was before, or you touch it like in a secure way. Because here we modified the free memory pointer, but here it's go like after the assembly block, we go back to Solidity and we don't um, tell basically Solidity or the EVM where the next free memory is. So we need to make sure, sorry, we need to update the free memory pointer. So we store at 0x40 the new, it's the new value. So basically we have 68, no, we have, yeah, we modified in total 68 bytes plus this one plus this 32. So we modified 100 bytes. So sorry, we add 100 bytes to the current free memory pointer. So we added 100 bytes of memory. So we're going to tell it that we added 100 bytes of memory. Now let's try. And yeah, and we're good. Okay, so our data is the same as what we had in Solidity. So it's all good. Okay, let's keep going. It's a bit long, sorry. And now we, okay. Now we are going to make our flash loan call. So we are going to, okay, let's leave it here. We are going to, again, same thing. It's always the same. It's a bit annoying, of course, but you store the function signature. Then you, again, we're going to write directly at the current memory pointer. So we want the new, so we are going to load the new. So this is not obviously like I'm doing a lot like of mcall and mload and mstore. This is not optimized. So right now the goal is mostly to teach you YUL. If you want to optimize it, you make sure you don't do the same calls. Like you don't need to, I wouldn't need to do that, but this is making it more clear. So I'm storing the function signature, then I'm going to hash it and store it at, again, this time let's not forget what we forgot before is at FMP we're going to store the size of the total call data that we are going to no, actually we don't need it this time. We need it if we want to log it. Yeah, let's store it. Let's store the size so we can log it, and I'll explain it to you as I go. Okay, so we will store the size. I don't know how big it's going to be right now, so I'm leaving it like that. And then add FMP. So if we do that, okay, I'm going to use hexadecimals. It's so 0x20 is the same as 32 bytes, but it's going to make it more clear. And we are hashing what's that? So 0. So we are hashing that, and the length is 40. Okay, so here we have a problem again. This is more than 32 bytes, and mstore, you can see it here, can store only 32 bytes. So this is going to store only the first 32 bytes. So we're not going to have the right function selector. So what we're going to do is we are going to cut it in half. So as you can see here, I have the first 32 bytes selected. So this is going to go on another line. Okay. So at index 0, we store this. And then at index 32, we store this. So it's the same thing, but we had to cut it in half. That's a bit annoying, but it's going to work the same way. So then at 0, and in total, it was 40 characters. So that's it. We have our function selector. Then okay, then we had 4 again. You remember because we don't want to override the first 4 bytes. So then we're going to store 0, then the player's address, then the token's address, and then the call data that we just computed before. So 0. Then we had 32, and we have the player's address. Then we set the token address. We had 32 again at 64. And then at 84, have our call data. Okay, now let's talk about like a new problem. So I told you before that bytes, they are encoded in two parts. In first the length and then the actual data. But when it's encoded in the call data, so you can again see it, sorry, here, how was it? Out of, no. Okay, I can't remember. Yeah, I can't remember where it was. You're gonna have to search for yourself. Argument encoding? No. Okay. You'll search it yourself, but I'm just going to tell you right now. So it's I'm going to since we have the call data here, I'm just going to log it and we're going to see what it looks like. I'm going to show you here. It's going to be easier to understand. Okay, so this is the call data for our flash loan function. So what does it look like? We have the first one, two. Okay. So this is the function selector. Then we have 64, so 32 bytes, sorry, of the first argument, then the second argument, third. So this is the zero. Remember, zero player token and call data. So zero, this is the player's address, this is the token address, and then this is the call data. So what does it look like? It first specifies the index in the call data where the argument is going to be stored. So 0x80, so it starts here. So here is 0, here it's 0x20, so 32. Here it's 0x40, so 64. Here it's 0x60, so 96. And here it's 0x80. So you see, sorry. So here, so it specifies that go check at the index 0x80 and there you will find the bytes. And again, that's the bytes we encoded just before. So this is the length of the bytes and this is the actual data that it's going to be used. Okay, so we need to add, so here, what we need to do is specify the index where our data is going to be. So here we are cheating a bit because we know what it's going to be, but you can just easily compute it since it's the fourth argument. It's going to be at 0x80. So 0x80. And then after 0x80, then we have the actual data that is approved call data. So now, again, I'm going to show you a special trick. So since we computed, yeah, let's do the trick. So we computed the call data before. So the call data is stored at approved call data in memory, basically. This is the address in memory. But we want to put it, we want to have all our arguments behind each other. So we want to put it just after here. So we're going to copy what was here to the end of our current memory. So to do that, we use a special trick, which is we are going to call a special precompile, which is called identity. So it's precompile number 4, and it's going to take as input some data and just return it. And since you know that when you return it, you copy the data to memory, basically it's going to be used to copy a chunk of memory to another place. Okay, so let's try this. So we are going to static call. So the contract we're going to call, the address is 0x4. It's the precompile. We are going to call it with, so we want it to start at approved data. The length of the data is going to be, so it's 3 arguments. No, it's the selector plus 2 arguments plus the size. So it's going to be 4 plus 32 plus 32 and plus before we had, you remember we had the size stored. So it's going to be 96. It's going to be 100. Okay. So we are going to get 100 bytes of data, and we want to store it here just after this. So we want to store it at that place. So at FMP plus 84 plus A4. So it's 32 bytes after 84. So it's going to be stored just after the 80 that we had here. And it's going to be 100 bytes of data that is going to be copied. Okay. And we don't care. I mean, it has to be successful. Otherwise, everything is going to revert. So we just pop the return value instead of doing let success. We just remove the return value. We don't care about what static code is going to return. And that's it. I think we are good. And then we are going to get our flash load call data. And we are going to check, yeah, and then we are going to check the size of our call data and update that variable. So the size is going to be, we had one variable, so 32 plus 30, okay, let's say 32, okay, and that's why actually I was writing it in hexadecimal, it's actually easier. So it's going to be 0x 20, 40, 4 plus plus 100. Let's do quick. That's what I do usually. I do, so we have 0x84 plus the data that we added. 0x, I feel like I'm missing something. Yeah, plus, it's not 0x84, it's 0x84 plus 100. I think this should be it. I think this is the length. This is the total length of our data. And then we are going to increase the free memory pointer by the same size, and the no, so 0x. So we add 32 to it because that's the variable that we have here. Okay, let's try. Okay, we forgot to declare. And let's log it. So this is good, and this is, it looks the same, but we added too much data. Add some extra value. So I must have messed up the count. Looks like there is, yeah. Okay, let's try it again. I need to recount, but okay, let's say it looks again, we are cheating a bit. We are using what we did in Solidity to make sure everything is right. And it looks like it's right now. Let's keep going. Okay. And I think, okay, so this is messed up also, but again, we don't care. It's just like it's going to waste some memory. So again, if you're optimizing, this is really not good. You should be careful. I mean, it's not too bad actually. Like it's just going to not use some memory, but it's going to waste a bit of gas. And then the last thing we need to do is um, call our flash loan function and then call our transfer from function. So let's call the flash loan function first. So let success call. So this time we use the call opcode. So call, it takes the address of the contract. So we call on pool. We pass it 0. Again, you go to evm.code and you'll check. We pass it 0 way, ether. And then we pass the data that we had. So this is the data. Actually, we don't need the length because this was this length that we stored here. We just used it. I just used it to console log it. But when it's in the call data, we don't need that length. So we are going to pass it. So we add 32 to it. Then, but the length, we are going to use it here. So this is the length. And then we are not expecting any return value. So we put 0 and 0. We don't want. We check that it was a success. If not, we revert. And let's go. Let's do it. Okay, it didn't revert. I guess it succeeded. That's good. And now we can just call our final function. So the transfer from here, token transfer from. Let me copy it. So I go back all the time. So we are going to, again, as usual, and store the transfer from. This time we have address and 256. And no, transfer from, it takes 2 addresses. So you can already see it's going to be over 32 bytes. So it's 37. So we are going to have to feed it again. Okay, we have, did I miss? No, it's good. Okay, so we have our transfer from hash. And then we are going to load again the memory pointer. So again, we are just doing the same thing. So it should be, by now you should understand how it works. We're going to store at the free memory pointer the hash of the function. Sorry, I forgot. It was 37, I think, in total. And then we're going to store at p plus 4 the address of the pool. P plus 36, or it's the same as 0x24. I prefer to write it in hexadecimal. We are going to store player's address, and then at 44, we are going to store. Okay, I think we should be good, and now we can just call gas. I mean, call the token and call the transfer from on the token. So let's load. We are almost done. I hope there are still a few people on the call. I can see, but I hope you are still here. All right, cool. And so we are calling, so we are taking the data from the frame memory pointer. It's going to be in total, so 1, 2, 3 slots, so 0x60, plus the 4 bytes of the function selector. And again, we don't care about the return value. Let's just um, discard it. We check if it's a success. If it's not, we revert. Okay. Okay, and it seems like it went well. Let's check. Let's enable the final checks again. Okay, and we're good. I think we solved the challenge in YUL.
Nice, bro.
I hope you liked it.
Can we? Yeah, that was really good. Can we take a look at the U code? Can you go back a little bit in
Of
the?
course, yeah.
Yeah,
Maybe I can send it somehow so that everybody
yeah.
can have it, because on the video it's annoying.
That was really nice,
But yeah, you can
man.
see it's a bit long. So again, like we encoded the call data, the data, then we copied it. I think that was pretty cool. That's a pretty cool trick that you can use to copy some memory. That's
Nice.
pretty useful. And then you make your calls, and you're good. But yeah, how do you want to? We will figure out like how to send the code. I can put it on GitHub, or if you have any other idea, whatever you
There's
want.
a organization on GitHub. I'll probably create a repository in there, and then you can just submit,
All right,
to
perfect.
awesome. Bro, that was really
Let's
good. Thank you so much for coming here, explaining this so well for us. This really means a lot.
all right.
I don't know. I learned a lot from today's session. And I want to know if anybody has questions. Sure, friend Ted.
Let me know. Yeah. I know it was a bit long, so I hope you were all focused. And yeah, I'm just seeing it in the chat. That's a good